Hi, ladies and gentlemen. Nice to meet you. I am Jian from Xi'an Jiaotong University. Today, I'm going to show you our work's input-agnostic hierarchical deep learning framework for traffic fingerprinting produced by our wonderful team. Let's start by looking at the background and problem description. People might wonder what exactly is traffic fingerprinting. In a typical traffic fingerprinting scenario, the user controls endpoints that access the internet. Meanwhile, the analyzer inspects the traffic with the goal of determining details such as device types, applications used, websites visited, or other design information. The analyzer's intentions can vary significantly. One could be an attacker seeking to compromise users' privacy, or one can serve as a security guard to detect network intrusions. The most common approach for performing traffic fingerprinting is to use machine learning techniques. In the first phase of machine learning pipeline, people collect data under a controllable testbed. For instance, in website fingerprinting, automated tools are used to direct browsers and gather corresponding traffic as samples. Here, each traffic sample is named as a trace. This slide shows a simplified example of a trace X, which corresponds to one website visit. The trace X consists of 3 flows, and each flow transfers different contents. A flow is defined by the IP 5-tuple, including protocol, source and destination IP address, as well as ports. It is worth noting that real traces are more complex than the simplified example, but it adequately showcases the trace structure. We can see that traffic samples are different from other types of data like images or videos. A traffic sample cannot be simply represented as a tensor or a tensor sequence, highlighting the heterogeneous nature of traffic samples. Suppose we have gathered a substantial data set. The next thing to do is to train a model. People started to use feature-based traffic fingerprinting years ago, but the feature sets are commonly task-specific, which means one feature set works on one data set but may fail on the others. The deep learning method has gained growing popularity due to its capability of automatic feature learning. However, the existing deep learning methods cannot appropriately handle the heterogeneous traffic traces. And our goal here is to build a neural network that can handle the heterogeneous inputs and learn the hierarchical structure that is naturally present in the traffic. Here is our system design. This figure shows the overall design of our framework. Given a trace X, the framework's objective is to predict the label probabilities. To support the heterogeneous input and perform the final predictions, the framework is structured at 3 layers that are the packet, flow, and trace layers. And our framework comprises 4 modules that are packet factorization module, packet to flow mapping module, flow to trace mapping module, and trace to label classification module. We label them from M0 to M3. The first 2 modules work at the packet and flow layers respectively, while the later 2 at the trace layer. Now let's dive into the design of these modules. The M0 module is to convert each packet into the packet factor. It is typically performed straightforwardly using the metadata of a packet. For example, packet timing and sizes could be factorized into the packet factor, since they are the most commonly available information when confronted with encrypted traffic. After being processed by the packet factorization module, the sequence of packets in one flow becomes the sequence of packet vectors. In order to abstract the packet layer information into the flow layer, the M1 module takes the sequence of packet vectors as the input and transform this variable length input into a fixed length flow vector. This process involves converting the individual packets information into a cohesive representation at the flow layer. It ensures that the resulting flow vector represents the instantial characteristics of the entire flow. In a given trace, the sequence of flow vectors represents the flow layer information, and the M2 module here plays a crucial role in abstracting the flow layer information into the trace layer. Note that the M2 module and the M1 module share a similar function and can use the same neural network structure. Finally, we have a trace vector that comprises the information of a number of flows. With this trace vector at hand, the M3 module employs multiple linear layers and a softmax function to predict the final trace label. In both M1 and M2 modules, we use neural networks to transform a sequence of vectors into a feature vector. Theoretically, we can employ various sequential models for this purpose. In our study, we construct 4 different types of neural networks, each belonging to a distinct family, which are the chain-structured, tree-structured, attention-structured, and hybrid family. To represent the chain-structured family, we use a bidirectional long-short-term memory neural network. For the tree-structured family, we designed a balanced binary recursive neural network. And as for the attention-structured family, we fine-tune the attention mechanism of the famous transformer. Lastly, we connect the chain-structured and attention-structured neural networks in series for the hybrid family. We also employ Xi'an compression in the M1 module to reduce the calculation. If we do not use it, the packet vectors goes in directly into the packet-to-flow mapping module, and we get a flow vector output. The amount of computation is approximately proportional to the length of packet vectors. After using the Xi'an compression, we are able to reduce the sequence length and thus reduce the calculation by several times. The next step we take is to address the issue of overfitting, which poses a serious challenge in the domain of traffic fingerprinting. Due to the limited availability of datasets in this field, obtaining large datasets is both challenging and costly. To address this problem, we adopt 6 techniques that are early stopping, weight decay dropout, batch normalization, auxiliary loss, and data enhancement. The first 4 techniques are commonly used in deep learning, while the later 2 are tailored for the traffic fingerprinting applications. The auxiliary loss is an additional loss used alongside with the main branch loss to optimize the learning process. Our auxiliary loss has 2 parts, and the left part is normally used cross entropy loss employed in the deep learning classification tasks. And the right part corresponds to the average value of the flow classification loss. Such hints are helpful because accurately classifying flows is beneficial for classifying traces. Data enhancement increases the size of a dataset by adding slightly modified dataset copy. We introduce 3 data enhancement methods suitable for traffic fingerprinting. The core print method randomly cuts a subtrace from the original trace. Noising randomly adds noise to the timing of packets, and the dropping randomly drops the packets with a certain probability. Besides being used separately, these techniques can be used in combination, which is a hybrid solution. Now let's move on to the evaluation. We used 5 data sets corresponding to 5 different tasks. 3 of them are public for user activity, fingerprinting, IoT device identification, and intrusion detection. And the last 2 data sets are collected by ourselves for keyword searching fingerprinting and Shutterstock's website fingerprinting. We can see that the result shows our framework achieves better or at least comparable performance for tasks where the SOTA methods rely on hand-acquired features. Next, we evaluate different neural net structures to see what the best structure is for traffic fingerprinting. And we change the neural network structures in both M1 and M2 modules. The results show that we should adopt the hybrid structures as they have the highest average macro F1 scores. We also performed another ablation study to test different solutions to handle overfitting. The slides shows the F1 scores using different solutions. Again, the hybrid method achieves better and more stable performance than the pure ones. Here is the last evaluation, and we conducted 3 experiments, HA 1.1, 1.2, and 2, to show the benefits of hierarchy awareness. These 3 methods are hierarchy on awareness. The results show that without hierarchy awareness, the performance degradation of deep learning is significant in tasks. So in conclusion, we took the first step in designing an input-agnostic hierarchical deep learning framework to seamlessly land deep learning onto traffic fingerprinting. Our framework successfully applies in various fingerprinting tasks where certain methods rely on handcraft features and deep learning is not easily applicable. Furthermore, we propose techniques to handle overfitting and analyze real-world factors that affect the performance in our paper. It achieves better or at least comparable performance with just one paradigm. Our datasets and code are available at GitHub. So thank you for your time and attention. Any questions?